Okay, thank you, Rachel. So, Teemu Järvinen is like proper Finnish pronunciation, and I'm from Finland, now in Vancouver, Canada. So, AtomsCalculators kind of started to shape up in like a year ago when we started to put on the first release, and then we are now new one. So let's have like a table of discussion. So basically, I'll go a little bit hands down. So I just show how to use it. The basic thing for most of the people is to just use the calculators, and then I say a couple of things about how to create your own calculators, and then stuff like that. Let's see how does the time go, but like this is the basic use way. So you just state out using AtomsCalculators, and then you have available those commands. The main principle here is that none of the commands have been exported, so you cannot directly call them at all. So basically that means that you have to call it like the way it's down here. That's pretty cumbersome, so you can do this one instead. And this is very close to that what you do with ASE. So I presume it's something that you have got used into. The basic format here, actually, I would like to note that all the commands start with the system structure, and the calculator comes after the system structure, and that's for all the commands. There are commands that do something else as well, but we will go for those later. This is actually now a working example. So here we are just building Lennard Jones calculator for argon, very basic stuff. So you can use it with this empirical potentials stuff that kind of like shows you how do you build the calculator. There's like a just give the Lennard Jones parameters and get the stuff. And then you have to build the atom structure, and this is actually an example of how to use the atoms builder that Christoph mentioned. That's basically the same kind of command you use with ASE to get the like a system. And after you have these two, you can just call out like this. And that's how it works. So basically with AtomsCalculators, you of course have now units based on unit full defined. So here you can see the energy unit. And the same way goes for forces and virial. Basic stuff. And then there are these kind of commands as well. So the main point here is actually this double command, so energy forces, virial, but I will briefly mention this forces call so that you know that it is exit. And note here, none of these are exported, so you have to either import them or use add the AtomsCalculators in front. But this is the non-allocating forces calculator. You can use it. I don't want to go for details for this one. And there's a way how you can actually allocate forces. So again, you start with the system structure and then the calculator. Basically, my advice, don't use that one unless you want to have a certain kind of unit for the forces. Because you can allocate the forces to whatever unit you want to have it, and then you get the forces of that unit. That's the easiest way to have forces in certain unit. But anyway, and then there's the combination calls. So this is how you call them. And this way as well. So you have basically, it's a named tuple now instead of like a value. So you have to get out there like the what you are after there. So the main point with this combination calls is that many of the calculators have optimized way to combine forces and energy calculation. Example for is potentials. If you just call in like energy forces virial, then that is much more efficient than calling out the three of them separately. And basic thing, if you do like molecular dynamics, you want to have optimized for energy and forces as well, because that's what you call out from the calculator. And side note, you can use the non-allocating ones as well. They work the same way as the earlier force one that I showed you, but try to avoid them unless you have some special need for them. They are there, but yeah. And then this is important thing. So the interface supports keywords for the calculation. And here's an example with this Lennard-Jones potential that we created earlier with the empirical potential. So there's you can have this kind of tuning on whether or not you use it single-threaded, multi-threaded, or distributed. And the point here is that it's an option. You don't need to do this, but it's like a nice way to tune things with the calculators. So you should. There are no like conventions of what something do. So here the executor is just something that comes out of this volts package, which is there for transducers.jl. That allows you to do this kind of easy way of multi-threading, single-threaded, and distributed way of doing calculations. And so the idea basically is that these are like calculator-specific features, tuning-specific calculator, not the calculations in general. But this is kind of like the option. And then there are these kind of utility functions. So if you want to know what is the energy output unit for your calculator, you can call it like this. The same thing goes for like a force unit and length unit. And then there are these ones. So if you want to know what's your zero energy for the calculator, you can just call it like this. These are mostly like useful for those who like to implement like a molecular dynamics package or some something fancy. And then there's this low-level interface. So the one that was there was basically the same thing that you get with the ASE. And the low-level interface now is a little bit different thing. It is meant to include something like automatic differentiation and something fancy features. So that's how you call it. So that's like the general type of like call. So you have a calculate command. Then you have a type that specifies what kind of calculation you're doing. Then you have system, then you have calculators, and then you have two new things, parameters and state. So basically this comes from Lux. So if you have know more about what the Julia Lux is, then go and look for this one. And this is basically like the calculation type now is either energy, forces, or virial. The parameters and state you can ignore. I will tell you later on what those actually are. But that's how you actually call it now with the Lennard-Jones calculator. This is exactly the same call as was the earlier one. So basically now the idea what you can here actually see is that like if you don't know what you are calculating, you can just have this in a type of the calculator as like a variable for function call as well. And, but here is the first state. You already know that the output not only has energy, but it also has this nothing state. Here it's nothing, but in some cases it can be something else as well. there's always state in the output in all the commands with the low-level interface. And the output is actually named tuple. And you could actually, this is a combination call now. So now you calculate energy and forces, you just put the types in a tuple and that does it. So here you actually already start to see that there's some flexibility with this way of doing than the other one. And if we look for the what's the out, like here we have this date, then what you can do actually here is that like this kind of example. So if you use DFTK calculator, it supports actually this one. So here the first call returns this one, and now the state here is not actually nothing anymore. It's a internal state of DFTK. It includes the phase function. So now you just put in the phase function for energy forces calculator, and there it uses the existing phase function to do the forces calculation, which is much more faster than calculating again the phase function. So that's the idea here, how this state can be used. So this allows some flexibility with the calculations in the background. And this is a bit side note here. I have noticed that some people sometimes try to use these kind of commands to use it. That's not how it works. These are keyword arguments because we are stating the name, so you have to use it as a positional argument. So it's the last positional argument or fifth position. And you have to put something for the parameters as well each time. You can put nothing, it's fine. It just means that they are using the default ones. You can also put nothing for the state, which means that it uses the default state. Whatever is the default state for the calculator. And parameters. I'm not sure are there actually anything that support parameters completely. Ace potentials, probably in the future, it's I think work in progress. We will probably hear something later on, or maybe here. But like basically there should be a support. But this is an example what it would mean. In case of Lennard-Jones, you could just put in Lennard-Jones parameters there. There should be noted that this style of interface is from LUX, and the reason why it is in LUX is to allow automatic differentiation. So the fact that you have the parameters here means that later on you can develop rules how to do the automatic differentiation. So that's the main reason for it to exist. Also, it allows you to do some flexibility by changing the parameters of the Lennard-Jones potential on the fly as well. But as I said, it's don't think anything has implemented those things. And these are the commands that allow you to interact with the parameters and the state. I think they are pretty self-explanatory. You can just get the parameters or set the parameters, and that's it. Yes. So that was the. How do you use the potentials? They are just simple ones. You just call forces and it's real. Maybe in the future there will be Hessian as well, and you will see. But now I explain a couple of things what you can do with the non-Julia programs. So first of all, ASE converter JL allows you to use all ASE calculators as AtomsCalculators. So there's the first bit of how do you use it. It's pretty simple. Once you go on the ASE Convert website, you can see how it is done. And then there's this one. So IPy, if you do not know, it is a program to do path integral simulations. ring polymer, molecular dynamics, and so on. And it includes a protocol for different programs to communicate. So it works basically that you set up a server and then you contact your calculator to the server, and then the server can do calculations based on the connection. And that allows you to connect to like various programs. So you can use CP2K if you want. You can use LAMPS, Quantum Espresso, WASP. In practice, almost everything. And this is an important thing. ASE has an IPI server, so you can connect Julia Atoms calculator to that server and use all Atoms calculators from ASE. So that should allow the collaboration currently. The documentation on how to do this is coming. Hopefully I will get it done in like during this workshop, so you can try it later on. But I have been using it, it works, so I know it's in a good shape. And in the future, we have a proper ASE calculator, hopefully. I have it on like a prototype. The backstory here is that Python only allows garbage collector from main thread to run, and Julia runs it on from every thread, and that means that the Python program will crash if you try to use Julia however you want. That has been fixed in like a later version of Julia Call from August, so we should have it now working. And then there's a Molsy driver which allows you to do MD as well. It's similar to IPI system, but hopefully that one is in future. So basically this would allow us to like interact with other programs really easily. And then I just mentioned there's this package called AtomsCalculators Utilities. This is the package that hosts that IPI interface currently. And there are some tools to do stuff around. So it's kind of like a playground now where you can test stuff that is not immediately put in the main interface and so on. But this is next thing, so writing your own calculators. So basically you can implement either low or high level interface. And there's a macro basically that helps you to do it. And this is now because there's some tricks to use the macro. So if you implement your interfaces, always put this using AtomsCalculators. Otherwise you are making for problems. And this is the thing that you have to implement. These three things. At least one of the energy forces of real calls. And then you have to specify energy unit and length unit. Forces unit is immediately taken out from energy unit and length unit. It's a simple thing to do it. And also I would just go and read the file that has the interface defined, so you can see what's all in. That's kind of like the best documentation I actually advise. But like this is like how you define it. So this is the high-level interface definition. And this is like now the important thing. You have to write the function AtomsCalculators dot potential energy. If you don't do this, when you use the macro, it will fail. Basically, out of this definition, the macro will then write the high-level call, and that's how we get it working. If you don't want to use the macro, then you have to write all the interface calls by yourself, and that's a bit tricky. So this is the warning. This, I think, is the most common issue when you try to implement the calculator. So this doesn't work. And notice here, there's no AtomsCalculators here, and that's the reason why it fails. And basically, the reason for this to do is that in this case, you haven't imported the calculate command, so you cannot write anything for that calculate command. It just says what's the calculate command. That's the reason why it is made to fail on this one. And then if you want to implement forces, you do it like this. There's nothing special, of course. I mentioned here that you have to have these keywords, where you take on all the keywords. You don't need to do anything for them. You just allow them to be there. And that allows the use of the keywords in the general sense. And combination calls. They are a specific, like general implementation for the combination call. It just calls energy calculation and force calculation and then the variable calculation if it is. So it is by default two different calculations. If you have a calculator that supports doing them in one call, then you have to write the command by yourself. Otherwise, it's not optimized. So it is just up to you. But I advise you to write the combination call if it's like reasonable for your calculator, because it makes faster the molecular dynamics. And this is how do you do it with the low-level interface. And here you note you need to have the state. So that's a must-have. Otherwise, it says that you are not having the interface correctly. And the last thing I mentioned is these testing tools. So there's a submodule called testing that includes these functions. And when you write your own calculator, please use these, because they will check that your calculator is according to the interface, and they will also tell you what is wrong with your interface if you are doing something wrong. Also, if you are using some new calculator, you can use these ones to test that is it implemented correctly if there are something going wrongly and so on. And with that one, that is the brief tour on AtomsCalculators. This is of course not enough for the documentation, and I can explain later on if you have some problems on. And also, if you feel like something is missing from the documentation, which is work in progress, please come and tell me, and we can hopefully implement them in the workshop.
Great, thanks, Teemu. We've got plenty of time for questions. So anyone in the room, or I'm on the Zoom here as well, and you can either raise your hand and unmute, or just drop it in the chat, and I can pass it on, whatever works.
I guess I'm not super familiar with ACE, but is there anything else in ACE that AtomsCalculators could implement?
Implement.
Is there any other kind of, I know they do all sorts of simulation and setup and stuff like that. Is there anything else you'd like to add to AtomsCalculators from
ACE? Yeah, well.
Sorry, yeah, ACE.
I guess this is kind of like, currently we are like trying to get the low-level interface to have some kind of shape and get a like feeling of how to use it. But of course, there's like this comes in like the question, where does all the ASE stuff like belong? Basically, like this. I think the AtomsCalculators part is only for the calculators, and interface is related to that. And maybe we like most of the ASE stuff is kind of like geometry optimization. And there's molecular dynamics, which is maybe more something that goes for Molly. So AtomsCalculators don't try to be ASE. It's just basically the calculators interface, so that we have a unified interface for the calculators, nothing else. And the fact that we can use the calculators on other programs, not in Julia, but like ASE and You can even use like Julia calculators with CP2K if you want, with the IPy interface.
Yeah, Chuck?
Thanks. Could you walk through what the process would look like if you wanted to compute another property that's not an energy of force or a virial?
Yeah, so let's go for the low-level interface. So basically, this calculation type. So you can implement your own calculation type.
And is that the idea that
Yeah.
that the downstream user would send it themselves?
Yeah. So basically, you could implement a calculation type that's called Hessian, and then that calculates Hessian. Of course, we could even have as a calculation type, we could even have a molecular dynamics integrator there if we want, and then that would move the system in time, certain duration, and so on. So there's lots of flexibility that we can do this. So basically, how we could say that the high-level interface is the one that people have used with ASE and stuff. The low-level one, it actually uses multiple dispatch, so you cannot implement this one in Python if you really want to try it. But it allows us to do so many things, and this is just kind of like the first step. And I personally advise you that try to use the low-level interface in your calculations. It gets some to use, so you can basically ignore the parameters and state. You don't need to do anything with them. You can call it without them, and it makes it a lot more easier. And once you get the idea what the states and parameters do, then you can go on and do the fancy special tooling with those things. So basically, I presume that in the future, we probably go for the calculate interface. Of course, if you know that you only need forces, then call directly the forces call. It makes your life more easier.
So one thing to add to this, so you might have a very specific application where you define a new calculation type in your package, and it doesn't have to live in AtomsCalculators, but then there are probably many people who would want to compute a Hessian. So you could find that you can make a pull request to AtomsCalculators to introduce new calculation types that are shared by everybody. But the idea is that you start in your own package with what you need, and then you contribute it if it turns out to be useful for more than one person to the interface package.
So the basic thing is that it is an easy way to extend the interface, and you can extend it for some specific way that your package has some meaning for it.
So do we think on a long enough horizon that AtomsCalculator would have a lot of different properties in it? I mean, maybe not too many, but 10, 15. Atomic stress, charges.
Let's see how it develops. Yeah. That is a possibility.
I have a question about the units. So if a calculator is written so that it's kind of unit agnostic, is there...
So basically, I will see this. Yes. So basically, here the unit is in electron volts. You can have it as Hartree, you can have it as joules, whatever. So the basic thing for here is that it has to have a dimension of energy. Anything that has dimension of energy is fine.
Okay.
And same for forces and virial. So virial has the same unit as energy, and forces then has the energy divided by length. And okay, here's actually not told, I didn't mention anywhere, but forces is a vector of vectors. So vector of individual force vectors for particles. And the idea is that it is a vector of S vector, so that you can also use it, reinterpret and consider it as a matrix. and then virial is of course a 3x3 matrix. And basically that would be it.
All right, let's thank Teemu again, and we have a 15-minute break, so we'll reconvene at 15:15 to hear from Michael about DFTK. Thanks.